Well, thanks for joining. I work in the product development for Multitenant. I'm one of the product managers, and a piece of the Multitenant development group has built the autonomous services in OCI in the Oracle Cloud. So what I'd like to do is just talk about how we're using Multitenant rather than describing, the individual features and functionality of Multitenant. Try to describe it more in terms of the components of a larger service, and then illustrate how some customers are using it. Those would be internal and external customers. So, I mean, just to recap quickly, it's the containerization of the database, where each of these hosted tenants are running in a hosting container database, which we refer to as the CDB. Each of these tenants are referred to as the pluggable database, and they're self-contained in that they have their own system, sysocs, data, table spaces, and associated data files, as well as their own undo. You can manage in the context of each of these individual PDBs, or you can manage as an aggregate, which we refer to as manage many as one. And when you consider database as a service at scale, you really will be managing operations as a single entity, as an aggregate, if you will, executing either patch, upgrade, or backups at the CDB root level, which would also capture the PDBs, again, as an aggregate. And then in terms of density, the fact that each CDB is elastic in terms of compute, where it's sharing CPU and memory associated with the hosted tenants. For our customers, it's basically was originally to consolidate, but what they've quickly come to understand is that they can standardize using Multitenant and automate. And database as a service really is about automation. Automation to make an environment predictable. And for Multitenant specifically, customers are using a collection of Multitenant / PDB specific features and functionality. And what I'm going to cover is just how we're using provisioning for our service, and specifically the online relocate, hot clones, and also I'd like to focus on the resource management profiles and lockdown profiles. And I'll touch a little bit about application containers and how how we're using some aspects of application containers and how our customer base is using application containers. But really, it's when you consider database as a service, it's about providing a predictable compute environment, not just for customers, but also for providers. So essentially what you want to do is provide a simple, agile, predictable, robust environment to your customer base, where they know what they're getting in terms of compute. And once you've bound the parameters of compute, it really becomes a much simpler bin packing problem in terms of consolidation density and efficiency of the hardware available to the environment. So in 12.2, we introduced hot cloning, and we have a pretty rich cloning environment to begin with, but now these operations are online, where the source is active, and we can hot clone off of that source for test dev environments or analytics, and just about any use case that you can think of. And you can hot clone in a single container database, or it could be remote, and remote could be geographically dispersed. So for example, in our own OCI autonomous services, we just recently introduced cloning, where we clone either within an availability domain for a particular data center, or across regions. And we can clone in parallel multiple PDBs simultaneously. And in fact, your first, as you're creating a PDB, that's a clone operation off of a template PDB, which is shipped with Multitenant to begin with. And that's the seed CDB, which is just a generic database reflecting the configuration of the container database itself. What we recommend for services, database services, is to create your own custom seed where you bake in certain requirements for the service. And that might be the different users or the application that you've got configured, where you can actually configure it in a seed so that every time you provision a database off of that custom seed, they have these things embedded in that database. Refresh is an extension of Hot Clone. Once you Hot Clone, you're immediately out of sync with the source. If you need to stay in sync with the source, particularly for test dev environments, we'd recommend a refresh. You would clone as a PDB refreshable clone, which is a hot clone, but then either through a frequency that you define or through a manual operation, you refresh it as of a particular point in time. So you can keep a source and a clone master, if you will, in sync through PDB refresh. And then with Relocate, and I'll spend some time on this in a later slide. Relocate basically allows you to online relocate a PDB from one environment to another and disparate container databases. And I'll illustrate in a couple of slides later how we're leveraging that for our own services for patching, upgrade, and workload balancing. The PDB Relocate itself is an extension of both a combination of hot clone and refresh for this relocate. And you could think of it analogous to a VM live migration, but only for the database pieces. So we're not copying over the operating system, but we're copying over only the contents of that particular PDB at the block level in parallel. So the other functionality that we're leveraging in our cloud is referred to as application containers. And we are provisioning application containers for certain applications provisioned in Autonomous. But what's interesting about this is that you can create an application schema and what's referred to as an application root, and then sync up application PDBs that are logically attached to that app root, where the application is replayed in the context of each of these PDBs. So effectively what happens is when we're building an application, we'll run the application create statements in the context of the app root. We'll capture those statements and replay them in the context of individual PDBs that you create. We refer to that as capture replay, and the operation in the context of an app PDB would be a sync operation. A critical component of our database as a service is basically the database resource management. And really, fundamentally, it comes down to these 6-7 parameters that are configurable both in the context of the CDB root, but also in the context of the PDB. And unless you're oversubscribing, the PDBs as an aggregate would be a subset of CPU count and memory for each of the different PDBs. So the fact that we've distilled the number of critical parameters that bind the compute specifically for a PDB shape allows us to do lots of things in terms of bin packing, but also dynamically modifying these parameters on the fly. So each of those parameters are configurable in the context of the PDB. What we do is, and this is what we would recommend for those interested in building databases as a service, is use the database resource management profile, which we refer to as performance profiles, which allow you to declaratively define particular shapes, in this case, t-shirt sizes, small, medium, and large, of a particular shape. So shares in terms of CPU shares, and utilization limits in terms of caps. So it is caps and shares which are applied to each of these different plans associated with a particular profile. So what that means is basically taking these shapes and defining the shares and utilization limits, which is basically a percentage of, in this case, CPU and memory, of the CDB definition. So you're defining a percentage of available utilization for memory and CPU, but then imposing limitations in the context of the PDB based on init.or parameters that you can define and lock down. So for small, medium, large, and extra large, you would be able to define and restrict execution and use of CPU and memory and the number of sessions based on these parameters for each of the different t-shirt sizes. So essentially what that looks like is for, say, the X1000, I could define a PDB lockdown profile for large and define each of these different parameter settings and ultimately lock them down, which is a declarative way to basically inhibit any modification, if you are without, lock down any modification of these parameters except for a privileged user. So that might be a common user with privilege, such as sys and sysdba, or a common user that you define that executes at the service level for your database as a service. And as I said, it's a declarative way to enable or disable certain functionality at the statement level. So in this case, I'm either enabling or disabling alter system, but that would be true for alter session. It could be true for alter database. Rather than granting privilege, which tends to be binary, where you get everything or nothing, we can grant you a subset of privilege in the context of the lockdown profile for statements, as well as functionality associated with options or packages. So we can limit exposure to the operating system through these resource management profiles. And this simple example of different shapes that I had shown you earlier. Another example is basically taking those parameters and driving a factor based on a percentage that you're calculating of the CPU count in the parameter, where you can derive the values based on the percentage of CPU count as allocated to the PDB defined by the CDB. So in this case, I'm only taking eight CPUs out of a total of 42. So basically taking that value as a factor and calculating it against the parameter values to get fixed values based on a simple single setting, the CPU count in the context of PDB. And this is something that's documented in a MOS note, which you can review and set your own factoring. The point here is that simplify the init.or parameter settings as much as possible. So are you following me? Well, we got a few others.
Yes.
Okay, great. I've unmuted everybody, at least I've tried to. If you have questions, just feel free to ask. Just jump on in. When you are considering, yep, was there a question?
No, I don't have, no.
Okay, so when you're considering database as a service, essentially you want to think of scale and ease of management at scale. And that usually involves some sort of fleet management. And ease of management would essentially also potentially mean some automation layer. And what we've done in our own cloud is to build an automation layer built on REST. And I'll talk about that in a minute. But essentially, there are a couple of components in the service that you want to be keenly aware of. One is defining those custom seeds for the service that I described, whether it's a data warehouse or an OLTP or a doc store or like a Taleo Business Edition CRM type app. You're going to build a template for that. And you want to keep the template specific to a particular service. And when a provisioning request comes in, you probably want to keep a metadata store like this central CDB, where we can do lookups in terms of utilization patterns across the environment. Now, in this case, we've got black, red, and amber pods. They may be in a single system, they may be across systems, they may be across availability domains in a region, for example, as is the case for our managed service. But basically, being able to define these templates and REST-enabled call into, via a web server, call into a central CDB to do the lookup in terms of what services are available, what pods or container databases do I have registered where I can provision based on the request that they're asking for. So in this case, they may be asking for a red application to be provisioned in the red pod. So it would actually do the lookup, store the data, and do a remote clone off of that seed. To give you an example of how we do it internally and the power of automation and the ability to encapsulate a somewhat complex workflow in an automation flow would be simply, a customer comes in either through a service console and via an HTTP request, passes in let's just say a provisioning request. Because we have JSON in the database now, we can construct and deconstruct JSON docs pushed between container databases. So the web server, by a JDBC call, could push out the JSON doc to the central CDB, which we break down, store as metadata in terms of who's asking for what and what's the shape of the PDB, what's the application, and then do a lookup on in terms of, okay, based on this request, where is the best place to provision that database? Then we pass that back into the web server, which they push the job to the target database as dictated by the metadata coming out of the repository. And then the provisioning request is executed. In this case, as illustrated in the earlier slide, we provision off of a specific seed for the service. We'd apply the service lockdown profile, which would include the definition or the shape of that particular PDB that we're provisioning. We'd lock that down so that not only are statement executions restricted, but also control of those init.org parameters that define the shape of the PDB are locked down. And then because this is our OCI, we impose TDE in the environment. So we rekey the tenant in terms of the TDE keys stored in a common wallet. And we'll open up the PDB and send those credentials, which is essentially how to connect to the database and what are the what is the wallet associated with the TDE key. So being able to embed a somewhat complex workflow in a simple provisioning request. You really want to automate as much as possible. We chose REST, invoking PL SQL on the back end. Whatever works best for you guys. It could be invoking SQL directly, or a shell script wrapper, or Python. In fact, the intent is that to be able to build an automation layer that can hook up with any pre-existing automation layer that you might have. So that could be Ansible or Kubernetes or something of that sort. And I'll show you some examples in just a second. Another piece that we've built that you might find interesting is the most complicated thing is getting out of building a database as a service, getting the most out of your compute. And that really depends on intelligent placement algorithms. So if you had standard shapes, then it potentially could be very simple. It's a bin packing problem where you just do round robin, and these tend to be predictable environments that maybe test dev or UAT, and it lends itself very well to oversubscription because it's predictable in terms of what the shape of that PDB may be. Alternatively, the shapes may vary either at provisioning time or at runtime, because with multi-tenant and the CPU count configured at the PDB level, that's a dynamic operation to basically change that CPU count on the fly without having to bounce anything. You can expand or contract the CPU size and associated parameters that dictate the size of the PDB dynamically. So it then becomes a little more complicated in terms of placement, and we need a different algorithm to determine where is the best place, and it's usually in terms of utilization on a node, the least used node. So those are cloning operations off of a custom seed that we do in our own managed services. In terms of how we're leveraging Relocate, I'd mentioned that we use Relocate for patching and upgrades, but also for workload balancing. And patching and upgrades may be at the database layer or it may be at the operating system layer. But basically, we have an algorithm that will determine what's the target container database that we want to evacuate. We do a quick calculation in terms of where is the most intelligent place to put those PDBs. In terms of perhaps anti-affinity rules or preserving the CPU count required by that particular PDB. But we scatter them so that we can evacuate the environment and patch it. We recover from that through a gather. So we may decide, okay, let's just roll through this environment and we'll bring those PDBs back and scatter the next container database and roll through the patch so that it's an online operation. The clients, the impact on the clients would be minimal. So some things to consider for database as a service, basically, what are the lifecycle management at the PDB level that you want to automate because you are managing at the PDB level. You want to create your own seed so that you can bake in certain features and functionality such as security so that every cloned image off of that seed has these pre-configured service environment. You want to, depending on your preference in terms of t-shirt sizes or dynamic resize capabilities for your service, you definitely want to evaluate some sort of intelligent deployment because it becomes important when you're trying to get the most out of your compute possible. In our case, we try to minimize the amount of inputs by using a factoring algorithm that I described. So it's just very simple for a user to come in and select CPU, storage, and the name of the database, and probably a password to connect as an admin user. We have other things associated that are available. So you could configure certain types for a particular pod if you needed to group. Things that you also want to consider is like hyper-threading, whether you're going to oversubscribe, how this might fit into pre-existing CDCI pipelines, and ultimately, when you're considering scale, what does that mean for fleet management? So we introduced something that we refer to as CDB Fleet, which gives you the capability of defining a lead container database, and then what we refer to as proxy PDBs, which are a PDB pointer into a remote PDB. And the fact that we now have this lead CDB and a pointer into proxy PDBs for a particular environment gives us the capability of executing very simple SQL across all these container databases, leveraging parallel query. So what's interesting about this is that parallel query tends to execute in the context of a single database. But because we have an aggregate of multiple container databases, and through this proxy PDB, we can execute parallel query across multiple container databases and hosted tenants. So that if we're, in this case, trying to select from PDB name, actually PDB name from CDB PDBs, we'd be able to see all hosted tenants in the environment. And this is really effective when you're trying to gather metrics or usage patterns or status of particular databases at scale through a simple SQL command across multiple tenants. So the last thing that I want to cover is what we've done for our managed services, which we intend to expose externally, is taking that concept of capture replay that I described for application containers and leveraging that for our own patching and upgrade. So basically what happens is a patch or upgrade is essentially a modification to the container database. And all hosted tenants in a CDB share the data, metadata of the container database in CDB root. So we patch that container database root dictionary once. We'll capture the SQL that's actually executed. We've done a low-level analysis of the patching and upgrade. As it's executing, we've discovered that there are a lot of no-ops that are executed that as a whole tend to consume a lot of time. So if we're able to capture the patching or upgrade that's actually executed in the context of that CDB root, then we can leverage the replay functionality through a sync operation on targeted PDBs. So in this case, an in-place capture replay would basically replay through a sync operation in parallel across all hosted tenants in that particular container database. This is very powerful and speeds up the whole patching and upgrade cycle considerably. In addition to that, you may want to manage the upgrade at the PDB level or the patch at the PDB level. So there may be some PDBs that you need to manage in terms of when they're ready to upgrade. So through a PDB relocate operation, plugging into from a 12.2 to an 18.4 CDB root, we're able to replay at open automatically the sync operation of that particular PDB. So essentially what we've done here is through automation and some level of sophistication in terms of our patching algorithms is basically to relocate a 12.2 PDB from a CDB root in one location to a CDB root hosting 18.4 binaries and associated data dictionary. And before opening that to a connecting client, we upgrade the data dictionaries through a sync operation automatically. So when it's opened, it's already been upgraded for you. Again, this is something that customers have asked for, and only through the fact of having to do this exercise several times in our own managed services were we actually motivated to do something about it and simplify the operation entirely. So what I'd like to do now is just kind of walk through some use cases, external and internal customers. So this is one that I presented at Open World with this past year. Swiss Mobiliar, basically we're migrating a monolithic schema consolidated database to microservices. And what they needed is a PDB at the back end that fits into their CDCI pipelines. And they evaluated a number of different databases and ultimately decided on PDBs, which is nice because that order get state is a REST call invoked through TeamCity, which is then pushed into the whole Docker build for the application layer via Kubernetes. And ultimately, I think it takes them, let's just walk through their timing, think ultimately it takes roughly 8 to 10 minutes for this whole cycle to build through. But ultimately what happens at the end, the connect string is pushed into the Docker image and returned to the requester so that they have the PDB up and open and they have the defined connect string available to them, all within 8 to 10 minutes. And this REST call is basically a REST that invokes a SQL script on the back end via a bash wrapper. This has been so effective for them that they found it very easy to build and tear down PDBs at considerable rate. So in this case, roughly they delivered 1,200 PDBs over the last 2 years. This is British Telecom, and they've presented on this also at Open World. This is a database as a service, but using application containers. And what's effective here is that if I were to create a database as a service, I would have to either give privilege to different users access to the root CDB to execute the clone operation. Because it requires, a generic multi-tenant requires the clone operation to be executed in the CDB root. What they decided was to build out application roots, which I referred to earlier as application containers, and use that as a grouping function for different lines of business, and grant privilege to clone in the context of the application root. And effectively what they're doing is delegating responsibility for the management of their container database, if you will, and all hosted tenants related to that container database to the line of business that owns that container database. So they still have a protected CDB root. They have a privileged user in the container database, either executed manually or through automation. In this case, BT uses automation that allows them to grant a sysdba privilege locally to this application root without granting sysdba or common user privileges up here. And that just illustrates the level of isolation that multi-tenant provides, particularly in this context for application containers. This is another project that I actually have collaborated on with a customer that is deploying an OCI using application containers. Their objective was basically to break out various business domains and the metadata and data associated with that, cleanse that and bring it in as an aggregate, cleanse it and push it out as schemas that map to specific applications relative to the business domains. What they want to do is provide an innovation platform to their partners that could come in via OCI connection to the app, an app PDB, where they can execute REST-enabled CRUD operations on these applications. So essentially what this is an application root with Apex installed in each of the different app PDBs and an Apex workspace in each of the app PDBs with an ORDS interface that allows their partners to come in and execute via HTTP REST calls to execute the CRUD APIs against these individual applications mapping to the business domains. And this allows them to partner up with, in this particular case, fintech partners that are trying to collaborate or build innovation for collaboration with various financial services. So for some internal use cases, focusing on ATP and ADW, this is an open service broker integration with ATP and ADW for a partitioned Kubernetes cluster where you've got Kubernetes masters hosted in an Oracle tenancy, but a customer tenancy could invoke via open service broker a call through an API to provision either an object store, actually any managed service in OCI, but in this case for the database, object store, ATP, or ADW. So in their tenancy, so being able to invoke via the open service broker a call into OCI to provision in their tenancy an autonomous database. Another one that is soon to be released is an enterprise cloud JSON Doc Store. And basically what they wanted to do is build a modern document-centric development environment, REST or SOTA-based APIs, which would include server-side in-database JavaScript procedures. And what they were going after was basically an enterprise database that provides ACID transaction properties and SQL-based reporting for analytics and parallel execution. So ultimately, truly an enterprise class database, which is the autonomous platform, which also provides elasticity, ingrained security, performance, and availability on Exadata. So they've got, target use cases which include microservices, but also some interactive apps and schemaless data on the back end, where they via REST will call in, create the autonomous JSON cloud service, and pass that back to as a peer service to the requesting JSON Doc Store client. So those were just some examples. That's basically what I wanted to cover. If you guys have some questions or would like precision on or detail on something, or even share what you guys are doing with Multitenant, I'd be very interested. Did you find this helpful?
I don't have a question. I think I need to look again because how I was working and I just listened, and I think I will look at another session.
Yeah,
better.
Yeah, so you could review this session. There are other multi-tenant sessions. You can get a trial environment in the cloud to basically create a multi-tenant environment in OCI, and play around with the capabilities. And there are some great partner blogs out there that just kind of walk you through different scenarios, different execution, different topologies. So I'd strongly suggest you query on your favorite search engine for multi-tenant Oracle database.
Yes, please.
Ahmed, Dina, do either of you have any questions?
Yes, Ahmed, yeah. Really, thank you about the fantastic session about the multi-tenant. My question is, I need more details about the algorithms that use to placement the PDB. Okay, so like I mentioned, it's an open API for configuring other algorithms, but essentially in our service we use two, and it does require those algorithms are round robin or a greedy algorithm, which is basically least used node. And there are certain things that you need to take into consideration. You need some sort of health check monitor at some frequency to know, and a metadata store that stores the different PDBs that you've created and in which server they're open. So for example, we run rack, and you can control where those PDBs are open. So it gives you a lot more flexibility in terms of providing elasticity in terms of compute across multiple servers in that cluster. But you can also keep track of, you would need to keep track of where those PDBs are open and how each of these registered servers or container databases are being used in terms of compute, so CPU and memory principally. So you've got some sort of health check monitor that's running at frequency. You've got a metadata store that captures state and the configuration. So what are the registered pods and what's their compute capabilities? And then the algorithm itself, which is basically evaluating that metadata
I have these many databases. Their current utilization in terms of CPU is this much. The provisioning request is asking for this much compute. Where can I put it? It gets a little trickier with the greedy algorithm because that we allow online resizing. So that's where having a mechanism to come to at frequency check to see what the utilization patterns are for these targeted environments, because it may change from one check to the other, and you need to account for that, and because it would influence your placement algorithms. So the greedy algorithm is mostly to address that context, but it's not just the placement. It's the checks and state and the target compute capacity that has registered with you. Does that make sense, Ahmed?
Yeah, it's okay. I'm just need to imagine how some customers, they want to scale up some resources and how that can to be in case of you don't have a much resource in the current server, how that will be reallocate without any downtime or interruption for the customer. That I want to imagine how that to be.
Okay, so the fact that the relocate or the initial provisioning?
I mean, in case of the customer, they are going to scale up,
okay,
for example, a CPU, but we don't have enough CPU on that compute node.
Got it. So that's what we would refer to as oversubscription. And there are a couple of ways to address that. You can define whether you're going to oversubscribe the environment or not in terms of CPU. Let's just talk about scaling the CPU. So if you decide to oversubscribe, then you probably want to define a ratio. So I want to oversubscribe no more than a certain percentage of total CPU times a factor 2 or 3. And then you once you've reached that limit, you need to inhibit any resize operations that are executed in that environment. And those are essentially attributes that you can configure in the context of the container database for your particular service. So then if you don't do anything, then you will just simply oversubscribe without control. If you want to inhibit the resize operation that would create an oversubscribed environment, well, then you define quotas for potentially that particular user, where he can resize his PDB, but only to a certain CPU count. Or you, and most likely you would define quotas for the entire container database so that you're sure that the container database doesn't oversubscribe. So programmatically, you can define these things both as an attribute of the container database, which DDL statement that you can define in terms of quotas. If you don't do anything, it will remain totally elastic for everybody to use, compute, and ultimately bring the server to its knees if you've totally oversubscribed. And then you can define also in the context of PDB so that the PDB users have a quota that they would respect. It's imposed on them as part of a lockdown profile.
Oh, okay. Yeah, thank you. Really, thank you. We don't have an internal document to get much information about this algorithm that using to placement the PDB. We don't have something internal we can get this information.
No, because it's possible that you can build your own, and the example that I showed earlier, which is why don't I just go back to that real quick? The microservices from Swiss Mobiliar, they have a data store. I don't think I copy it here, but it's part of this workflow, this register. They're registering both in the Docker registry, but also they have a repository that captures the request, stores the request attributes in terms of the size, and they just do a round robin. Nothing sophisticated. They set quotas. They wrote it themselves in combination of shell script, defining the attributes of the container database through SQL and this REST interface.
So this algorithm as well, we are using the same with the autonomous for ATP or AW, the same algorithm?
Yes, but a little more sophisticated, completely automated, and as I said, it's extensible. So there are other things that attributes of a request that we would need to consider. So, for example, OCI allows you to tag a provisioning request. Well, that tag we need to be able to consume, and the tag might define the provisioning request to deploy in a specific region or a specific availability domain in a region, or to be co-located with a particular application. So, that adds another dimension to the entire placement policy. And it gets complicated very quickly depending on, how you're consuming tags, what you're consuming. That needs to be negotiated with, the application tier or the OCI group.
Okay, got it. Thank you.
You're welcome. Anything else? Do you guys use multi-tenant?
Yeah, it's interesting. I think all the technologies that are coming in the cloud is built on of multi-tenant.
Yes, a lot of them, because it just gives us the ability to isolate the database without losing the agility to relocate it, move things around.
Yeah, I got it. Yeah, even the autonomous ATB and ADW are using the same algorithms as a pluggable database on CDB.
Yes, but again, because we own the service and we own the PDB code, we can do a lot of things to enhance that service that in the core database engine itself. That sometimes we may expose it publicly, sometimes it may be engineered systems only. Because ADW and ATP are running on Exadata.
Yes.
Exadata is a predictable environment for us. We know how to do things much more efficiently, and we can make certain assumptions of the environment that we simply couldn't do if we were to just step out and run on any kind of platform.